Have you ever wondered how you just click the button and everything comes together? Just show you this video. You didn't have to think about electrons, logic gates or machine code that is happening behind the scenes. This is the magic of abstraction. In computer science, abstraction is the art of hiding complexity. It's about creating layers where each layer provides a simpler interface to the messy details below. Every time you send an email, tap a screen or stream a video, you are standing at the top of an incredibly tall ladder. Let's climb down and see what's underneath. At the very first level, we have pure physics. Computers are made from transistors, tiny switches made from silicon. This is where the abstract meets the real world. Most transistors today are MOSFETs, which stands for metal oxide semiconductor field effect transistors. A MOSFET has three terminals: the source, the drain, and the gate. When you apply a certain level of voltage to the gate, then only electrons can pass, which exactly works like a switch. Millions of these switches, each just nanometer wide, works together. At the next level, we have logic gates. Combining transistors, we get gates like AND, OR, NOT, XOR, and so on. An AND gate also is true only if both inputs are true. An OR gate outputs true if either input is true. To simplify the design process, each transistor logic gates are represented by the symbols. Now combine millions or billions of logic gates and you get something remarkable: a processor or CPU. Inside a CPU are components like ALUs, arithmetic logic units for calculation, registers for fast storage, caches and memory controls for managing data. This level is called computer architecture. Engineers here don't think about electrons or single gates. That complexity is hidden below. Now we reach the first level of software, machine code. These are the raw instructions that processors understand. Binary strings of zeros and ones. This is what the hardware actually executes. Every CPU architecture has different sets of instructions. A program written for one architecture doesn't work on another. To make programming more manageable, we added another layer called assembly language. Instead of remembering every binary string, we write short mnemonics like move, store, load. This instruction maps directly to machine code, but it's readable enough for humans to reason about. Assembly was still too low level for a programmer, since programmers have to understand every aspect about CPU architecture. That's why C was created. C allowed programmers to write code that looked more like human logic and less like CPU instructions. At the next level, we have operating system. If you want to create some applications, you need to write everything from scratch, managing everything by yourself, like I/O devices, processor, memory, etc. It is abstracted by OS. It provides standard interface for hardware. But even with C and operating systems, writing programs was still complicated. Developers kept repeating the same work, so higher level languages like Java, Python, and JavaScript were created. These languages hide many low-level details like memory allocation, system calls, and CPU-specific behavior, so developers can focus on solving problems instead of managing hardware. At the next level, we have libraries and frameworks. These are collections of pre-written code that simplify even more complex tasks. Want to process images? Import a library. Build a website? Use a framework. Behind these abstractions lie thousands of lines of code, all condensed into simple reusable tools. Finally, we have applications at top where most people interact. Click, drag, type, tap. Beneath these intuitive actions lies an immense hierarchy of abstraction, from user interfaces down through frameworks, languages, architectures, logic gates, and ultimately physics itself. All that complexity compressed into a seamless experience.